Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, thank you very much. So Sebastian, I've got 15 minutes, right?
15 plus 5, yeah.
15 plus 5. So I'm going to try to squeeze a 4-hour tutorial into 15 minutes, which is going to be really hard. But actually, rather than doing that, I'm going to be focusing on one or two main topics. So indeed, this is a quite large piece of work. Some of you have already seen this before, but hopefully I will show you something different this time. It's about forests. They have become very, very popular in machine learning, in computer vision, and also lately in medical image analysis. And so what a lot of us, not just me, but a lot of us have been trying to do is build a unified model that tries to explain how forests work and across the many different papers out there, so that we unify all the work, but also once you've done that, we try to push forward and try to figure out how else forests can be used. And so hopefully today, in these few minutes, I'll try to give you a flavor of this.
But I thought, I don't know anything about machine learning, but I look at the ASCII book, and I thought they already explain how it works and why it works and all the business.
Yes, but mostly for classification. Okay, 95% of the work out there is on classification forests. What we call decision forest is a slightly more general term, which allows us to do all these other things as well. So, like I said, 95% of... Sorry again?
It's really different from...
Yeah. Especially the last three things. So, what you find in the literature is mostly classification forest. You find very, very, very little work on regression forest, and the work you find there is, I think, never probabilistic. In regression forests. If you find a paper which does regression forests in a probabilistic way, which doesn't come from this lab, please point me to it. But then, as you will see soon, we try to push the model to be able to do other things as well. So effectively, we try to bridge the gap between supervised and unsupervised machine learning, and also, as you will see, between discriminative models and generative models as well. So hopefully I'll be able to show you some of this. All right, I'm going to skip a lot of the stuff. So classification forest, we have talked about it in the past. It has been used in Kinect and in many other places as well. Regression forest, as you saw earlier from Jamie's talk, is also been used in something which has the potential to do Kinect sort of things as well. And I'm not going to talk too much about it in this talk. What I will be focusing more is on density forest, and so figuring out how we can use forests for constructing compact representation of a probability density function, learning this probability density function from unlabeled samples, from unlabeled data. But other things that we do describe in our work, which, by the way, is available right now as a Foundations and Trends journal paper, is also how this work can also be used for manifold learning and how it relates to more conventional manifold learning techniques. And finally, we also show how you can bridge the gap, really, put together supervised and unsupervised learning, making use of the fact that we can discover densities of data in their higher dimensional feature space, in conjunction with a few label points which may be expensive to get, and do semi-supervised learning. So I'm going to skip a lot of stuff, and I'm going to concentrate mostly, like I said, on density forests. So let me get there just a sec. I'll get there. So it's, yeah. So this talk is not much about application. It's more about the sort of efforts we've been doing towards modeling forests and unifying all the work has been done out there. But the density forest is slightly new. I haven't seen that done before, especially in this kind of way, and it's all very experimental. So first of all, it is about generative models. We're going to construct a compact model from where I will show you we will be able to generate random samples according to a learned distribution. So I realized that in this audience, all of you are really keen in movies. So while you were talking this morning, I had to put in a movie. This is one of my favorite ones. It's 12 Monkeys. And the reason why I put it in is because, the reason why I put it in is because it's the best explanation of generative models I've come across so far. So let's see, this is a sci-fi movie, and what Brad Pitt will be explaining to you in a minute is how you can use generative models to predict what people are going to do in the future. Okay?
No problem. It's probably just another kidnapping featuring Jeffrey Shrink. Pardon me, ain't that X Shrink? This is your leader? A certifiable lunatic who's holding former psychiatrists all his plans for God knows what wacko irresponsible schemes, and now God knows what she's written out there on that wall. Who cares what psychiatrists write on walls? I think I told her about the army of the 12 monkeys. Impossible! Do you know why? Do you know why? Because you pathetically ineffectual and pusillanimous pretend friend to animals. I'll tell you why. Because when I had anything to do with her 6 years ago, there was no such thing. I hadn't even thought of it. Then how come she knows what's going on? Well, here's my theory on that. When I was institutionalized, my brain was studied exhaustively in the guise of mental health. I was interrogated, I was x-rayed, I was examined thoroughly. Then they took everything about me and put it into a computer where they created this model of my mind. Yes, using that model, they managed to generate every thought I could possibly have in the next, say, 10 years, which they then filtered through a probability matrix of some kind to determine everything I was going to do in that period. So you see, she knew I was going to leave.
So that was it. So I'm going to explain now to Brad Pitt how this probability matrix of some kind works, right? So let's imagine we have a set of unlabeled points here on the left. These are represented in a very high-dimensional feature space. So what we want to do is we're going to build a set of trees. They are going to be trained randomly, which what they're going to do effectively is, in a way, they're going to cluster this space in ways which make sense, and we will define what this make sense is. You will see very soon that the algorithm for constructing these trees, it has got very direct links to expectation maximization, for instance, with one of the main differences that this is hierarchical. So just like in expectation maximization, you have this iterative process where you try to fit, for instance, some Gaussian representations to the data. The same thing we're trying to do here, and we stick for simplicity with Gaussian representations. But the way in which the data is split is hierarchical, and each of the internal nodes represents a binary split of a subset of this data. But in order to make this work, we need to define an energy function, a cost function, which for us is always a sort of information gain. So this is sort of the glue of this model, the thing that allows this model to work so many across so many different settings and tasks as well. Because what's interesting is that, as we know already, information gain and the related entropy function can be defined both for discrete labels or continuous labels, can be defined both in the supervised cases where we have labeled data attached to our training set, and unsupervised cases as well. So in this case, we were talking about no supervision, just the feature representation itself. And so how does this information gain work? So for instance, if again, as a working assumption, we assume to work with Gaussians for each of these partitions, then we can use the standard definition of a continuous entropy defined for Gaussian distributions, which is defined in here, and is nothing else than very intuitively a function of the size, the volume, if you want, of these blobs. So splitting this ensemble of data into two blobs is convenient or not, depending on whether we gain anything from the sum of the final volumes compared to the original volume itself. And so actually, yeah, here we go. Here we have an example of what this information gain tries to capture. So imagine that we have this data set before the node, and then we're trying to split it. So before the node, in the set S, we have a certain Gaussian, which is this blue one, and a certain entropy associated to that Gaussian. And if we decide to split the data with a horizontal split, which intuitively clearly is not a very good choice, what we end up having is two child nodes, the green and the red ones, and the two Gaussians associated to those are very highly overlapping. This is an indication, a visual indication that the split is not very good. The information gain in this case, quantitatively, is about 1. And if instead we use a more reasonable split, like the vertical one, we obtain two Gaussians which are much better separated, and this is reflected into a much higher information gain. So this is just to refresh your memories, really, on how information gain works for unlabeled data in a parameterized setting like this. So we can do this for many different trees, and so what happens is that when we at each node we choose those features which produce the highest information gain. So at each of these split nodes we'll have certain what we call weak learners, or split functions that could be axis aligned or not. And eventually at the leaves, a certain number of training points will arrive at those leaves, a certain number of clusters, and each of these clusters is represented with a Gaussian. Again, we stick to Gaussians. But when we train a forest of trees, each of the split nodes will be trained with some level of randomness, as is standard practice when dealing with random forests. Another alternative is to use the bugging technique, which we can use in here as well. There are at least two ways in which we can inject randomness. And so now that we have many different clustering trees, effectively, where at each leaf node you have a different Gaussian representation, what is the final density function for the whole forest? It is given by this. It is just a linear combination of Gaussians. So that's why this model is, it is this one. It's a linear combination of individual tree Gaussians. And so you can see that this is in the way in which it looks. This is very similar to a Gaussian mixture model, but again, there are differences not only in the way the training is done, but also in the fact that each of these Gaussians is actually domain bounded. So it lives only within a certain well-defined domain in the feature space, and this will become clearer a little bit later on. Of course, when talking about generative models, there is always the difficulty of figuring out what the partition function is, so as to make sure that the probability is correctly normalized, and it adds to 1. And this can be worked out. It's not too difficult to achieve, at least in certain situations. The situation being that you have axis-aligned split criteria in the split nodes. If you have more complicated weak learners, then it's a little bit more difficult to achieve. But this is, for instance, the output of a single tree applied to a square 2D domain. So you see the Gaussians which are bounded by these sort of quadrilaterals. And this Z partition function makes sure that the volume subtended by this entire surface sums to 1. So I'm moving a bit quickly because I would like to show you some examples. So this is, for instance, very simple. This is a very simple toy example. We have in a 2D feature space, we have two blobs, and we train different trees. This is different forests. This is what happens when we train a forest with depth 2, very simple stumps, depth 3, depth 5, and we use axis-aligned split criteria. So in this case, of course, we get nothing else but a sum of two Gaussians. In this case, we get extra splitting, and here much more splitting. So as always, when looking at forests and when looking at many other machine learning techniques, we need to be careful with the possibility of overfitting. So we need to be a little bit smart there. And this is what happens during testing. So now what I'm doing is I've trained my 3 forests from the few training data I have, and now I'm trying to compute the probability density function P of V for each of the points, not just the training ones, but also everything else in this white square. And so you see what the difference is in terms, when you go from shallower trees to deeper trees. In this case, we achieve a very clear overfitting. On the left portion here, you see, it's not playing correctly. The left portion, you see the output of an individual tree. On the right portion, instead, you see the output of the entire forest. So you see this averaging effect being achieved over the output of individual trees.
I thought, maybe I'm mistaken because I'm reading on anything like this, but I thought like random forest didn't overfit when you use bootstrap and your business.
It's not true that they don't overfit.
Isn't it what they say in the ST book?
Sorry again?
Isn't it what they say in the ST book?
I don't know what they say in the book.
Using bootstrapping and all that?
It's not true that you cannot overfit with forests. You can overfit with forests very badly indeed. In fact, there are, as we make it very clear in our book, which should be coming out in less than a year or so, there are two main parameters which control the behavior of the forest. One is the number of trees you have in the forest, and the other one is the depth of the trees. Now, what is true is that with the number of trees in the forest, you cannot overfit. Like if you have 1 million trees or 10 million trees, it doesn't matter. The more you have, the better. Of course, there are computational implications. But with the depth of the tree, you have the usual overfitting sort of sweet spot. So you need to be very, very careful. In Kinect, for instance, at least in the first instantiation, Jamie used trees of depth 20. And because the data is so complex, we haven't reached overfitting yet. But perhaps if we use depth 30 or 40, which would be computationally intractable, I suppose, then we would see degradation as well.
It doesn't have anything to do with the sampling strategy?
Sampling of...
Again, I'm naive, but I read the chapter.
Yeah.
And I thought the bootstrapping thing was the key to not doing...
Yeah. I mean, the fact that you have randomness definitely alleviates, as you can see here, it alleviates the problem, right? And therefore, how you incorporate randomness, how much you sample, in what way you sample, will have different effects on the generalization, i.e. on the overfitting problem, absolutely. And we do investigate this at length in our own book. So I welcome you to have a look at the book and tell me what you think about that. We do an investigation of that. The amount of randomness and the model of the randomness have got a huge effect. And I would say that perhaps the amount of randomness that we call rho in the book is probably the third most important parameter in forest. 2 minutes. Okay. What should I do then? I'll show you some results like spirals. We love spirals. So in the previous case where the data was so simple, we were very easily achieving overfitting. This case, which is a little bit more complicated, if we use very small stumps, we achieve underfitting, and trees of degree 6, of depth 6, seem to be working a lot better here. But I wanted to, so we have comparisons, quantitative and qualitative, with respect to EM, with respect to randomized EMs, multiple EMs, GMM EMs, and all sorts of things. But what's cool, I think, is that all of this theory corresponds to very simple algorithms for actually sampling. This is a true generative model. So from certain data points that you have seen earlier, we have learned some compact representation of this PDF. And now using the tree structure alone, by traversing the trees in a randomly, in a guided random way, let's say, you can sample points, which is what has been shown in these animations. So we don't sample from these images, we sample from the tree, using the structure of the tree. And this can be used, for instance, to solve these sort of problems where you have ambiguity. This is, if x is my input variable and y is what I want to obtain as an output, my dependent variable, this is a mathematical relation, not a function, because there is ambiguity here. Ambiguity occurs all the time in computer vision. So if as an input I have x, I would like to estimate y, I want to make sure that I capture the nature of the ambiguity in the data. Now, if I use a regression forest, because a regression forest can cope most naturally with functions rather than mathematical relations, we cannot do that. But if instead go through this density generative model, we can do this. So, if I had, given an x, a fixed x that was here, we would be able to obtain the output conditional distribution, which will look like this for different values of x. So you obtain a proper multimodal distribution for the conditional. Now this is all rushed because I don't have time, but like I said, there is a lot of material. You have all the slides already available from the computer vision web pages. You have a technical report. You have the foundation and trends paper. And now we are writing a book with Springer, where there'll be a lot of invited chapters by Pascal Foy, Roberto, and many other top researchers who have experience with forests. And in the book, we try to show how these different peoples have effectively used this model, though they probably didn't know they were using this model, for many different applications, both in computer vision and in medical image analysis. I think it will be a really nice piece of work, and I welcome you all to give me comments. Questions? Yes, Toby. Toby is writing the code for the book, so there will be code made available. He's promised me.
Given that I probably shouldn't be asking silly questions, can you explain why it would be not correct to sample from the density image, why you have to sample from the tree? Because
it's a much more compact representation. Now, when you are in 2 dimension, in this toy example, yeah, you can sample from that, discrete quantized distribution, and it's very easy to do so. But here we try to be a little bit more general, and so when you have a real scenario, you have much higher dimensionality, and you cannot do that, right? So you cannot do this. So sampling from the tree by traversing the tree from the root to the leaves, which is an algorithm I didn't explain, but it's very efficient, is the best way to do. Yes?
So when you train, you don't talk about it much. When you train the trees, do you optimize sort of each node?
Yes.
Okay. Is there a global cost function that you minimize, or?
It could be interpreted as minimizing a global cost function, which is related to this information gain.
Is it sum over all the nodes? Or?
Correct.
Okay.
But actually, the way in which the optimization works is greedy, right? So you make local choices, and that's the one of the many things that is not fantastic about trees. So in theory, you could think of redoing all of this, but in a more Bayesian way, where rather than deciding in a hard way whether to send the data point to the left or to the right child, you send it to both with different weights. So it's a typical Bayesian way of doing things. But in practice, you would find it a lot more difficult, computationally, to optimize things, to train things, and to test them as well. But some people like John Wynne here are thinking about how to do that in a sort of compromised way that achieve some of the flavors of Bayesian trees, but maintain some of the speed of this sort of techniques.
All right.
Thank you very much.